My name's Darlene True-Christ, and I'm the Community Engagement Manager for OOI. And I'm really delighted to have this panel of experts before us. Thank you all for coming. First off will be Suzanne Carbotte, and she's the Bruce Heason Senior Research Scientist at Lamont Doherty Earth Observatory at Columbia. Thank you, Suzanne, for coming. And Bill Chadwick, who's a research professor at the Hatfield Marine Science Center at Oregon State University. Thank you. And William Wilcock, who's professor of oceanography at the College of the Environment at the University of Washington, who is currently sitting in Hawaii in quarantine, waiting to get on a ship. So we're really delighted to have these experts come and share their information. So thank you again, and I will switch it over to Suzanne.
All right. Okay, I will share my screen. How does that look? Can you all hear me? Okay, and you can hear me okay. All right, great. Thanks, Darlene and the OOI team for the opportunity to talk about our recent research concerning the magma plumbing system beneath axial volcano from marine seismic imaging. Let me just get rid of this. Okay. All right, so Axial, it's located on the Juan de Fuca Ridge, where new oceanic crust of the Juan de Fuca Plate is made. Axial has been the site of focused investigation for over 2 decades, and during this period, 3 documented eruptions have occurred, with OOI instrumentation in place for the most recent of those eruptions in 2015. From this history of observations, we know a lot about Axial's hydrothermal systems and about the eruption dynamics. The main magma reservoir beneath Axial, that is the heat source for the hydrothermal systems and the melt source for these recent eruptions, has been characterized using multi-channel seismic data published in a paper by Arnouf et al. In 2014. Arnouf made use of 2D multi-channel seismic data that we acquired in 2002. And from this study, the data reveal a broad main magma reservoir that underlies the caldera. It extends north and south of the caldera limits for about, it's 14 kilometers in total length, about 3 kilometers in width. It's located about 1.5 kilometers beneath the seafloor and is about 0.5 kilometer to 1 kilometer thick. The seismic data indicate that there's variations in melt content through this magma reservoir with more melt-rich portions and more mushy portions. And in this schematic interpretation of the main magma reservoir, we see displayed the shallowest portion of the reservoir is located beneath the south central part of the caldera, and this is the region where it appears to be most melt-rich. In a study that we published last year, we report on the discovery of a deeper melt still conduit that underlies this horizontal main magma reservoir at Axial. We made use of data from the same seismic survey as used in the 2014 study, but examined previously unprocessed sections as well as deeper parts of the previously processed sections. The panel on the right shows 2 of these sections. This one here in the top is from the line located here that goes along the center of the caldera. And then the bottom panel is the line crossing the caldera. Both of these, we see the bright reflections from the top of the MMR. The interpreted location of the MMR is highlighted with this blue dashed line. But we're seeing beneath the MMR, we're seeing a series of deeper subhorizontal reflections forming this vertical conduit. These reflections are spaced roughly 300 to 450 meters apart, and they extend into the mid-crust about 5 kilometers beneath the seafloor. Mapping their location in map view, the location of the sill complex is enclosed by this red sort of elongated oval shape. This is roughly 5 kilometers long by 3 kilometers wide and located in the south central portion of the caldera. Given the location of these subhorizontal reflections within the beneath the MMR, where temperatures should be very hot, we are assuming that temperatures are in the 1,000–1,200 degrees centigrade region here. So these events are locating to what's presumed to be the mush zone beneath the MMR. Based on similarities between the characteristics of these reflections and reflections that have been modeled, the axial magma lens reflection that's been modeled at cleft segment, we assume we're inferring that these events arise from thin magma bodies, maybe a few tens of meters thick, that are embedded within a low melt percent mush. We've examined this melt lens conduit in the context of the eruption history at Axial, based on studies of the 1998 and 2011 eruptions. Chadwick and colleagues in 2013 find that both of these eruptions initiated in the same location. The eruption initiation site is indicated with the red stars here superimposed on the outlines of the erupted lavas. Based on time series signals associated with the 2015 eruption, it is also interpreted to have initiated from the same, roughly the same location. Depicted here is the interpretation of the MMR and the interpreted locations, the initiation sites of these eruptions. They are inferred to have initiated from this region where the main magma reservoir is shallowest, where melt content is highest, and it is this region that is underlain by this stack of vertical this vertical section of subhorizontal melt lenses. So our melt lens conduit here, underlying the inferred source region for these eruptions, we are inferring that magma flux, magma recharge in this melt lens pipe was linked to the initiation of these 3 eruptions. We are extremely fortunate at Axial to have a long-term record of volcano inflation from seafloor bottom pressure recorders that spans the 3 eruptions. This is the inflation records shown here from Nooner and Chadwick that they published in 2016. And this is for the 1998 to 2015 interruption period, with the events corresponding to these abrupt deflations, the eruption events. Nooner and Chadwick have modeled the pressure records from the suite of sensors located on the caldera floor, shown here, and obtained a best fit pressure source that corresponds to a steeply dipping prolate spheroid centered at 3.8 kilometers beneath the seafloor, and roughly the top terminating about 1.5 kilometers, so roughly coincident with the top of the main magma reservoir. But this spheroid, importantly, is lying mostly below the main magma reservoir. So this pressure source has the same vertical geometry and same depth beneath the MMR as our melt sill conduit. It is offset from the sill conduit in terms of its geographic location. The best fit source is locating here at the in this Nooner and Chadwick model at the southeastern edge of the caldera. However, a study published in 2020 by Hefner and colleagues, which is revised modeling of the inflation records that also includes the effects of fault-induced deformation. The best fit inflation source has the same general geometry, but moves in location to this central portion of the caldera, central western portion. Superimposed on our melt sill conduit, the center of the inflation source moves roughly to the center, the northern edge and the center of our sill conduit. New results, however, that are going to be presented tomorrow in a session at AGU tomorrow afternoon by Hefner, Nooner, Chadwick, and their colleagues. In this presentation, they are presenting new deformation models for an inflation record from axial derived from repeat AUV bathymetry data. And these new results are showing that the best fit source has a geometry more similar to the subhorizontal main magma reservoir beneath axial. So different inferences regarding the inflation source. Additional insights regarding volcano inflation at axial are derived from the patterns of microseismicity detected with the OOI and pre-OOI ocean bottom seismometers. So this is the left panel here shows results published in Wilcock et al. 2016, showing the pre, co, and post 2015 eruption microseismicity, the spatial distribution of that microseismicity, and a subsurface cross-section through the caldera in this region here. We've superimposed this microseismicity on one of our sections showing the deep meltlands conduit. All of the microseismicity is located to above the MMR, and it's on these outward facing ring faults that have been inferred. Mapped, when we look at the seismicity in map view and compare it to the plan view of our sill conduit, the seismicity is located roughly, it's concentrated along the eastern wall of the caldera and the western wall, but there are two diffuse bands, one here to the north across the caldera floor and another to the south here. And this north band is roughly coincident with the northern edge of our sill conduit, and the southern band going through the sill conduit. So we're attributing, our interpretation is that these seismicity patterns are consistent with a component of fracturing of the shallow crust linked to inflation centered within this sill conduit. Okay, the findings of a deep conduit composed of stacked melt lenses raises the question of how melt accumulations within this hot mush zone beneath the MMR might have formed. There are a number of different mechanisms that have been proposed that could give rise to formation of subhorizontal melt lenses in a mush. These include intrusions at permeability barriers. So there may be, for example, changes in rheology with melt accumulating at these boundaries. Accumulations could form via remobilization of mush, so conversion of mush to melt through a recharge event from the subsurface. And another possibility, which has long been proposed for ascent of melt within the mantle at mid-ocean ridges, is melt segregation due to mush compaction and the development of porosity waves. At axial, the long-term record of steady intereruption volcano inflation that's documented from the geodetic records is consistent with ongoing porous flow of melt during magma recharge at depth. And we favor this third mechanism. To further explore this possibility, we conducted numerical models and for melt ascent within a mush matrix, and for plausible values of the melt and mush viscosity and of the melt fraction. This is results from a 1D numerical model. and we find the development of zones of higher melt fraction, quasi-regularly spaced, that have a similar spacing as the melt lenses that we're observing in the seismic data. Second to last slide here, I just want to make a call out to the 3D multi-channel seismic imaging of Arnouf and his colleagues. They conducted an extensive survey in 2019 that is going to provide a full 3D image of the magma reservoir, both the shallow MMR as well as this the deeper sill conduit that we imaged. Preliminary results from this study show that there were several other smaller deep sill conduits beneath, including one beneath the vent field that was discovered in 2011 when the OOI cable was being laid, another beneath the shoulder of the North Rift Zone, and another beneath the northern portion of the caldera. So finally, just a few thoughts on future research directions and needs for additional instrumentation at Axial. Our preferred model for the vertically stacked melt sills is that they may be segregations from a mush zone due to compaction, but it's also very plausible that these could be forming as sill intrusions with periodic dike intrusions bringing melt up through the lower crustal melt column. Existing seismicity observations show that all the seismicity is above the MMR. We're not seeing any seismicity within the melt sill column that could be reflective of deeper dike intrusions. But the aperture of the existing seismicity arrays is quite narrow, and very interesting would be broader seismic networks that are capable of resolving and characterizing any deeper sub-MMR seismicity. Also of a lot of interest would be broader geodetic networks to monitor for dike intrusions and inflation signals across the volcano, including these other deep stacked melt sills that may be magma recharge conduits in other portions at Axial Seamount. Okay, and I will stop there and take any questions.
That was great, Suzanne. Anyone have questions? You can raise your hand. Looks like you covered it. Every time I had a question, like, how are you going to resolve the origin of melt sills with mush? You gave, you have three options, and then you worked through to find a solution. You still have a lot of work to do, though.
Yes, no, it's highly speculative that these are much compaction features, but I think it's providing, the observations are worth further investigation, and additional seismicity studies that could really be looking at that deeper part of the lower crust would be really important to help resolve how melt is ascending within the lower crust.
It's great to have you and your colleagues here collaborating. All of your big brains are looking at these complicated issues and working together. So that was really encouraging.
Yes, we're learning an awful lot at Axial. And I guess I'll just make one final point, and that is that we really have a unique opportunity at Axial with the availability of real-time monitoring of volcano dynamics, which we can integrate and look at in the context of this high resolution imaging of the magmatic system that we can get from marine seismic imaging. And we just we're never going to get that kind of resolution of the magmatic system in any volcano on land. It's just not feasible. So we're going to learn a lot from this new 3D study and integrating it with everything that people like Will and Bill are learning from the inflation records and from the seismicity.
That's great. Well, thank you very much. And
okay. All right, so I will pass it next to Bill.
Oh, sorry, Suzanne, we do have a question. I didn't see it. How much can you say about where the next eruption will be? Is the OOI infrastructure in jeopardy? Ooh. Sorry, we almost overlooked that one.
Well, the magma reservoir imaging does show a real concentration of melt within this south central portion. The top of the MMR is dipping in this region. It does look like that has been a really important initiation site for the eruptions, but I think I would defer to my colleagues in terms of what they're seeing. They're getting a lot of information about inflation that's very, very relevant to this question.
We'll pose it to them as well.
Okay, so passing to Bill.
Okay.
Thank you.
I'm just responding to that question. I'd say we don't know, where it's going to erupt next. If I were to guess, I would say it might erupt on the North Rift Zone again, just because the 1998 and 2011 eruptions went south, and I think fewer intrusions and eruptions have gone north. So maybe it's, has more room to accommodate another dike intrusion. But who knows? Well, we don't have really any way to know what it's going to do next. All right, I will go ahead and share my screen here. Let's see. There we go. All right. So following on Suzanne's talk, I'm going to talk about how the OOI monitoring data of deformation and seismicity is illuminating some new results, some of which we're presenting at this meeting. So my talk here is sort of a preview of a poster that I'm presenting tomorrow at AGU. If you're here in person, you can check it out at the poster session tomorrow afternoon. And if you're online, I have an online version of the poster too, so you can check that out. Okay, but let's see, gotta advance, there we go. All right, so this is a cartoon of Axial, and as Suzanne was telling us how magma is supplied from beneath the caldera. So that supply of magma, which appears to be pretty much continuous at Axial, at least in the last 20, 25 years, the effect that has is as magma is supplied to that reservoir, it actually bows up the roof of the reservoir, the seafloor, and we can measure that uplift of the seafloor with pressure sensors. And this work started, 20 years ago in the 1980s with autonomous battery-powered instruments that we call bottom pressure recorders. And when the OI cable came to Axial, part of the instrument suite is 4 of these bottom pressure recorders that also have tilt meters in them. So that's part of the suite of the real-time data that's comes back on the OOI cable as part of the regional cable observatory. So that's data that I'm very interested in. So as the seafloor gets uplifted with time during an eruption cycle or a deformation cycle, as the seafloor gets more and more uplifted, it's stressing the crust more and more, and that generates earthquakes. So the deformation, the magma supply into the reservoir, the deformation, the earthquakes are all sort of related, and this talk is trying to figure out, how they're related and what we can learn by looking at them together. And I should have started by acknowledging my co-authors, who that includes William Wilcock, who's going to talk next, and he's really the earthquake expert. But we've been collaborating together, and you know, one of the strengths of OOI is that it allows between people with different expertise, and I think that's one of the things that I've enjoyed the most about OOI. Anyway, so after the volcano inflates, it can't do that forever, because eventually, basically, the magma chamber, the edge of the magma chamber breaks, and a dike is intruded. So when that happens, pressure is released from the magma chamber. The volcano deflates, the seafloor subsides, and lava comes out somewhere. So that's kind of the cycle between eruptions. So here is a view of what has happened since the last eruption in 2015, which is on the left edge of the plot here. So we're plotting two things here. In black is a histogram of the number of earthquakes per day. This data comes from William. So the big black bar on the left is leading up to the 2015 eruption, when there were actually thousands of earthquakes per day. This plot only goes up to 300, as you can see. Then right after the eruption, the rate of earthquakes dropped way down to, you know, maybe an average of 10 a day for several years till about 2018. And then the rate of earthquakes started to pick up. And since then, it's been maybe up to a few hundred a day, but quite variable. And so in comparison, in blue, with the scale on the right, is a measure of the inflation deflation, or the vertical movements of the seafloor in meters. So you can, let's see if you can kind of barely see, this is inflating right up to the point where the 2015 eruption starts. Then the seafloor drops way down to zero here. You know, these are arbitrary numbers, but so right after the 2015 eruption, you can see the rate of reinflation was quite high, over a meter a year rate. But then since then, that rate, just, you can tell by the slope of this line, has gradually decreased. And until recently, the rate of inflation is less than 10 centimeters a year. So an order of magnitude slower. So it started quickly reinflating, and over time it's gradually decreased. So the text at the top here says, you know, on first glance, the two are don't seem very related, at least just thinking about the rates, because here the rate of inflation is high, the rate of seismicity is low. Later, the seismicity picks up, but the rate of inflation is decreasing. So what's going on? And William's going to talk about this in more detail right after my talk, so I won't go into too much detail. And Suzanne showed this too, but just a note about where the earthquakes are. And as Suzanne mentioned, and William will go into more detail, they're mostly under the west and east sides of the caldera. And they're in these outwardly dipping zones above the magma chamber, so between the magma reservoir and the surface. These arrows here are the edges of the caldera here. So we're looking across a cross section like this in this plot. And just to relate it to my cartoon, you know, this is kind of the big magma reservoir, and what Suzanne was talking about. As magma is coming into this thing, which happens between eruptions, then it's pushing up on the crust above it, which causes the inflation we see on the seafloor. And that deformation increases the stress along these faults and causes all the earthquakes. And there's probably other faults that link these to the faults we see at the surface, at the edges of the caldera, but they appear to be mostly aseismic, but they're probably both moving. So let's see. So we found that what seems to be a helpful way of relating deformation to the seismicity is a model that was proposed by Chris Kilburn in several papers. And it kind of works like this, that he's mostly suggests paying attention to the total deformation and not. So on the x-axis of these plots is total deformation over time. And so as deformation is proceeding, the stress in the crust is increasing. And if it were elastic deformation, then it would just follow a straight line like this dashed line. But what happens in the real world is that as the stress builds, there's some small but growing component that is inelastic deformation. And that effectively, that is the number of earthquakes happening. So with time, as the deformation proceeds, we should expect more and more of the deformation to be accommodated by fault slip or earthquakes until it reaches some critical stress, and then things change. So on the right here is the number of earthquakes basically versus deformation. And this model by Kilburn predicts that it should follow an exponential increase. So in other words, the number of earthquakes should exponentially increase with total deformation. And when we look, that's actually what we see at Axial Seamount. So this is the cumulative number of earthquakes since the 2015 eruption on the y-axis, and on the x-axis is cumulative uplift, basically. So data is in black, and the red curve is an exponential best fit curve. And another way of seeing the same thing is plotting the number of earthquakes per meter of uplift, and that also follows this exponential relationship. So back to the Kilburn model. So that happens up until this critical point when things change according to his model. And after this critical stress, then basically more and more of the deformation is inelastic. And so the model expects that the relationship between earthquakes and deformation should change to a linear relationship. And so we've gone back and looked to see whether we see that in the OOI data before the 2015 eruption, but it's a little bit hard to tell because we only have a few months of data. The OOI observatory came online in the fall of 2014, just about 6 months before the 2015 eruption occurred in April 2015. So we don't have as much data to look at, and we don't know the total amount of deformation, and it because it's limited, it maybe doesn't establish as clear a relationship as it would be possible if we had a longer time period. But so this is the same sort of plot with number of earthquakes versus cumulative uplift just from November 2014 to the eruption. And it could be exponential the whole time. This is one possibility, or this is the same data with dividing it up into 2 time periods where up until mid-March, it's this part of the curve could follow an exponential curve, and then afterward it could be linear. So it's sort of unclear whether that change from exponential to linear occurred at Axial, maybe. But we're going to try to look for that. Now that we're monitoring during an entire eruption cycle, we can look for this with more robust data, and this could potentially be a new forecasting tool that will be interesting to see if we see that or not. So another way of using this relationship to attempt for forecasting when the next eruption might occur is looking at extrapolating this exponential relationship. And so like the current rate of earthquakes per meter of uplift is 1.7 times 10 to the 5th. That's basically this dot. And and looking at the data before the 2015 eruption, that's about 17% of the rate of 1 million earthquakes per meter of uplift just before the 2015 eruption. So, you know, if we expect to see something similar, that needs to uplift, that the critical level of uplift is about 2.8 meters, and we're currently at about 2.1. So that means we've still got a ways to go. And given that our current rate of inflation is quite low, that means that the next eruption is still quite a few years away. And that's kind of the same story we get just by looking at the pattern of inflation and deflation from previous events, and assuming that the pattern is repeatable and you know, helps us forecast. The 2015 inflation was reached about 30 centimeters higher in 2015 than in 2011. So it's not exact, and we might expect the next eruption to have to go a little further still. So right now we're right about at the 2011 threshold, but again, the rate is very low, and so it's going to take a while to get up to 2015 and even above. And one thing that I've been doing is with the OOI data is I've got a website where the pressure data is plotted in near real time, and once a day we extrapolate the inflation rate from the last 6 months and project it into the future and figure out when we're going to reach the 2015 threshold. And since, you know, the inflation rate changes with time, so that that forecast date has changed with time also. And that's shown by this histogram that's color that early on in the reinflation in purple here, the dates were early because the inflation rate was very high. And as it gradually decreased, these forecast dates have moved further and further in the future, sort of like a carrot moving ahead of us. So the current dates are, you know, 4 or 5 years out just to reach the 2015 threshold. And so another way of looking at that same thing is this is the average rate of uplift since the 2015 eruption. This is averaged over a moving window that's a year long, so it's really smoothed out. But so you see right after the 2015 eruption, it was quite high, and it decreased, you know, rather rapidly. Then it sort of plateaued for a while. Then in mid 2019, it dropped again. Mid 2020, it continued going down. And so this part of the curve is just this part since 2015 eruption. So this is going back even further with our non-cabled BPR data. Blue is again, the average rate of uplift averaged over a year time window, going back 20 years. And the red curve, you know, from a deformation model, we can put numbers on the magma supply rate that basically follows this inflation curve. So looking back further over 20 years, you can see the magma supply rate, the inflation rate was quite high. After the 1998 eruption, it waned over the next decade or so, then increased leading up into the 2011 eruption. Between those 2011 and 2015, it surged quite a bit. So we think there was basically a surge in the magma supply during this time period. And then since then it's been waning. So, you know, overall it has this pattern of waxing and waning. So I am hoping that we have another period of waxing magma supply in the near future. But what the beauty of the OOI is we can keep track of axial every day and see what's happening and do this kind of real-time forecasting. So the take-home story is, yeah, OOI data allows us to continually track what's happening at axial in terms of the deformation and seismicity, and it helps us understand how the volcano works. And advances attempts at eruption forecasting, which, hopefully could have positive implications or consequences for trying to forecast eruptions in other places on land even. So just want to end with some acknowledgements. Thanks to the National Science Research, Deb Kelly, and the OOI team at University of Washington and the OOI data management team, because I'm certainly taking advantage of all their hard work. This work, the data I've shown came from the bottom pressure tilt instruments on the OOI cable. And if you want to find more information, I mentioned my poster, which is tomorrow. And this work is also going to be presented in a paper that's almost impressed at G-Cubed. And we have a preprint online at the Earth and Space Science Open Archive. And the website I mentioned with the real-time bottom pressure tilt data has at that URL. So that's it from me, and happy to answer any questions.
While we wait for people to raise their hands, I'd just like to say, wow, this is so exciting. I was unaware that you were that close to being able to really forecast what's going to happen at Axial. So,
well, it was easier when the inflation rate was higher, because like between 2011 and 2015, it was really inflating quickly. And so, it was kind of the case where something had to happen soon. And we were able to we made a forecast window within the calendar year of 2015, and it happened. So yeah, Axial is a kind of place where you can try to do this without having to worry about false alarms, because nobody's living at the base of the volcano. And so you can try forecasting and see what happens and not be too worried if you're wrong.
well, that sounds like you have years to perfect your forecasting.
Yeah.
But John Trowbridge has a question, so I've just allowed him to talk.
All right.
Hi, Bill. Thank you for a great talk. That was really interesting. I'm not a geophysicist, so this might be naive, but is there any mechanistic understanding or hypothesis about the waxing and waning of the inflation rate? In particular, I'm wondering if it's driven by a local process or maybe some larger scale process that's much bigger than the seamount.
I don't know. I scratch my head about that. I don't know if Suzanne has any thoughts, but it's, my thought is it's must have something to do with how magma is generated in the mantle beneath axial seamount, and whatever processes are happening, it's maybe not, just continuous at the same rate. It's somehow cyclical, and maybe it's it's either how magma is generated or how it moves up in the system to the shallow reservoir where it can erupt from. But Suzanne, do you have any other thoughts? I don't know how to explain it.
Yeah, I mean, I guess sort of with our thoughts that there's a mush conduit with melt percolating up under buoyancy, and they would be variations in the melt and mush viscosities that could impact the timescales of inflation. So if we get pulses of recharge that change the melt viscosity, then we might expect that there's different rates of inflation that are associated with porous flow on the subsurface. But that's wild speculation.
John, do you have any further questions, or?
Thank you for that. Appreciate it.
Great question. It's on my mind too. What is happening? Why is it doing it like that?
Anyone else? Last chance. Thank you, Bill. That was really great and exciting work. And so, William, we're on to you.
Okay, great, thanks. I'll share my screen. Okay, so I was going to talk about earthquake studies at Axial Seamount, and both Suzanne and Bill have talked about those a little, but I think my emphasis will be somewhat different. And I actually wanted to start going back in history, because for about nearly 2 decades, we had this incredible record of seismicity up to about magnitude 2.5 that was occurring off our coast from the US SOSUS, the US Navy SOSUS hydrophone array. And that was due to Chris Fox and then Bob Ziak, Bill Chadwick's colleagues, and basically taking advantage of the fact that earthquakes in the ocean generate T phases, which are phases that get trapped in the SOFAR channel, in the sound channel in the ocean. And that was extremely useful for understanding, the sort of patterns of seismicity we see on ridges. And one of the things they captured was the 1998, the first known eruption, the first observed eruption of Axial Seamount, where pretty much from when SOSUS was turned on in 1991, started recording swarms of increasing size that continued for about 6 years till the volcano erupted in 1998, and then resolved the migration over about 2 days of earthquakes from the summit of Axial Seamount, 40 kilometers down the South Rift. And so it's in the context of the sort of long-term observations of Axial Seamount that the OOI observatory was installed in the summer of 2014. And shortly after that, the geophysical network came on. And it really is a pretty impressive network, fairly small footprint, but there are 7 seismometers there, 5 short period and 2 broadband, as well as bottom pressure and tilt instruments that Bill's talked about. And right from when, it's important to sort of realize this is again showing one of Bill's plots, but when this was turned on, the volcano was inflating very rapidly. And Bill, Chadwick, and Scott Nooner had made a prediction that it was going to erupt pretty soon. And sure enough, as soon as we turned it on, there were a large number of earthquakes. And I don't think I fully appreciated their prediction at the time. But there really were an incredible number of earthquakes, and there were sort of seismologists who were looking at these on at least not quite a daily basis, but on a weekly basis, and looking at the number of earthquakes increasing from initially hundreds to thousands. And then I think the eruption was on a Sunday, because I remember because I was there working. And there was this seismic crisis in which there were probably tens of thousands of earthquakes, of which we managed to sort of locate about 9,000. And then rapidly, shortly after that, the seismicity decreased quite quickly, and is now, as Bill showed, has started to increase again. And these are plots that have been shown before, but the majority of the earthquakes were beneath the 2 east and west walls of the caldera, and they form these outward dipping faults. And these faults basically reverse. So during periods of inflation, the center of the caldera is going up. And then when it's erupted, it goes down. And I'm not showing it on this plot, but Samuel Levy, who was a student of Del Bonensteel, actually showed that with focal mechanisms. And to me, a very surprising finding, maybe it didn't surprise some people, of the eruption, were there also a second kind of very impulsive events that we recorded. And these were events that occurred at the sea floor that propagated in the water column. And what you're seeing on the lower left-hand plot are basically a series of echoes of that are basically bouncing up and down in the water column from some kind of impulsive event on the sea floor. And these events started pretty shortly after the seismic crisis. On the same day, the eruption was on April 24th, and by the end of that day, these events had started, and they continued for about a month. And it turns out that these are either steam explosions or implosions, we think, that occur at sites of erupting magma. So either water's getting trapped under lava, and then it form steam and that explodes, or possibly steam is trapped under the lava and then it collapses when it cools. And you can locate them from the spacing of the echoes and the directionality of them. And these have provided a remarkable record of the eruptions that Del Boonensdael and his student looked at, and then more recently Sau et al., where you can actually see where these explosions are and relate them to where the lava is erupting and the lava fronts. And that's really cool, because that means that in real time from this observatory, we can not only detect there's a seismic crisis and eruption going on, but you actually can see where lava is erupting on the sea floor. Now, the seismic network has some limitations, largely because it's quite small and it's sitting on top of this enormous magma chamber. And that means that for many directions, if you have earthquakes a long way away, you can't see them very well, because the seismic arrivals have to travel through the magma chamber, which is very attenuating. And that means we don't see many earthquakes up in the northernmost part of the caldera, and we don't know whether that's because there aren't many or because we just can't detect them very well. And the network also didn't observe, or barely observed, any seismicity associated with the propagation of the dike to the north. And that really means that we would like to sort of enhance the network, or enhance the techniques we have to be able to see that for the next eruption. Well, one approach is to basically reinvent SOSUS, noting that both the OOI cabled array and the Ocean Networks Canada-Neptune array have a large number of hydrophones on them. And so in principle, we could reinvent or re-implement hydroacoustic monitoring. And we did this for one day of the day of the eruption, and showed that we could successfully detect those earthquakes, the propagation of the dike, using the hydroacoustic phases. And it's probably not something I'm going to do, but there's a whole bunch of younger people who are very interested in machine learning. And so developing some sort of regional cataloging of hydroacoustics so that we could have SOSUS again is, I think, something that we should take advantage of these cabled observatories to do. What we are doing is planning with Maya Tolstoy and Felix Waldhauser at Columbia. We're funded for a 2-year deployment of ocean bottom seismometers to enhance the network. Now, as Bill has explained, the rate of inflation is decreasing. So when we were writing the proposal, we were extremely concerned that we wouldn't get it funded and deployed in time for the eruption. And then shortly after, when we got it funded, we thought we were about right. And we've now postponed the deployment for a year. It was going to be 2021. We're now in 2022. We'll have them out there for 2 years. And we can't keep on postponing, because there's a limit on how long NSF grants can last. So we will probably go ahead and do that this summer. We will record thousands, probably tens of thousands of earthquakes, and we'll be able to address, the deformation in the North Caldera. We also have broadband seismometers out on the flanks, specifically to try and look for deep, long period earthquakes that we might expect to see associated with magma recharge that Suzanne's been talking about. And if we're lucky, it will erupt in the next 2 years. I'm certainly hoping for a waxing magma supply. Now, if it doesn't erupt in the next 2 years, we were initially thinking, well, we could ask NSF to extend our deployment for a year. On the case that we were on the grounds, it has to happen soon. But if it's more like in the next decade, I don't think we'll be able to keep an OBS network out there for that long. So one idea that I'm really excited in is to try and use a new technology called distributed acoustic sensing. And so this is this really amazing technology that basically sends pulses of light down a fiber, optical fiber, and looks at what's scattered back. And then if you do that repeatedly, you can see changes in the timing of what gets scattered back through interferometry. And it turns a fiber optic cable that can now be up to about 100 kilometers long into basically a long line of something that's akin to broadband seismometers spaced maybe 10 meters apart. So it's absolutely fantastic technology. And we have done a test of this on the OOI of Pacific City during a shutdown last month. And we're waiting for the Navy to screen the data, but I think it's going to be really exciting to get that. But if we laid a custom cable around the caldera, we could essentially deploy thousands of seismometers and connect this to the OOI and have a network that would then last for the duration of the observatory and would capture the next eruption. So that's one thing that really excites me. Also just learned that Dana Manalang and I are funded to deploy a small network of 4 acoustic ranging sensors, shown on this plot by stars, so one on either wall of the caldera. And so these will basically talk to each other acoustically, and because they're high up, they can see each other acoustically, and then we'll have 2 on the floor. So these can be basically used for acoustic ranging for horizontal direction. So it will really complement the vertical geodesy that's been going for a long time. Potentially also can see temperature variations because the speed of sound changes with temperature. So we may be able to monitor sort of hydrothermal plumes with this technique. And one thing that really excites me is that one of these acoustic transponders will be connected to the observatory. So it will return data in real time, but we'll also be able to collect data from the other acoustic transponders. So we will get this data, you know, in near real time. And thinking further in advance, this can potentially be used for experiments where you communicate acoustically with autonomous underwater vehicles, and you can control them, collect data from them. And you can imagine that in the very long term, you might be able to station an autonomous underwater vehicle there, which then could respond to the next eruption, given that we will know where magma is erupting on the seafloor because of these explosions that come from it. And you could basically direct the autonomous underwater vehicle to go there, look at what's happening, and potentially collect samples. So that's basically, I think, everything I want to say in terms of things that I would like to do or will be doing. Thank you.
My apologies, I lost my cursor. That was great, William. Your thinking ahead is just pretty fabulous. You know, your broadband seismometer network. Really can't wait to see how that unfolds. But I'm with you that I'm hoping for an eruption by 2024 too, so we can have this forecasting that's successful. But
yeah, and I hope, like Bill, it goes north so it doesn't threaten the infrastructure. But
true. John has yet another question. Here we go. John, you're permitted to talk.
Thank you. Great talk, William. I really enjoyed it. Everything's exciting, especially that distributed acoustic sensing, I think is a real opportunity. But I just have one question about the last piece of technology. You mentioned, I think you said you're going to look at distance between the hydrophones that are talking to each other, but it's also the speed of sound is impacted by temperature, obviously. Is it possible to separate those two things, or does that have to wait for future advancements?
I think we may be able to, because the deformation of the volcanoes occurring relatively steadily, so that short-term variations will likely be related to temperature. If you go to the very deep, quietest part of the ocean, sort of thermally, acoustic ranging is accurate to about 1 millimeter per kilometer. If you go to places, where the physical oceanography is more complex, it becomes 1 centimeter per kilometer because of unmodeled temperature variations. At Axial Seamount, the uncertainties may be even larger because there is a lot of hydrothermal heat going to the water column. But we're lucky in the sense that the rate of deformation is quite high. So over a cycle, we're going to see meters of deformation across the caldera. But yeah, I think the short-term variations, we will be able to get information about temperature.
Okay, thank you.
And particularly if you had redundant paths with this four acoustic transponders isn't very many. And we'd love to have more and expand the network. And then the more redundant paths you get, then I think you can potentially get temperature and separate that from the sort of large scale deformation field.
Yeah, you'll be doing acoustic tomography of the
Yeah.
hydrothermal flume pretty soon.
Pretty amazing technology. We had on the OOI website the other day that RCA had just picked up a swarm of earthquakes and in real time. Have any thoughts about that, William?
Yeah, those were earthquakes on the Blanco transform faults. So those were recorded very well. They're quite a way away from the seismic network, but that's something that I think the hydroacoustic observations could potentially do a lot in terms of pinning down their location very well. So I think there's still a lot to do with this data being collected from this observatory. So I'm always very excited and wish I was younger and had more time in the day. But it always done. But.
Well, the three of you.
The shaking from the earthquakes on the Blanco, I could see in the bottom pressure and tilt instruments too, just because the seafloor at Axial was shaken in response to those earthquakes on the Blanco.
It's pretty amazing that you can see all this stuff and you're on the surface. Well, I'd like to thank all of you. It was really fascinating, and it's really moving toward better understanding and forecasting of what's happening down below. So thank you. But I have also been remiss in Deb Kelly is the PI of the Regional Cabled Array. She had a family emergency and she was supposed to moderate. So we shall send Deb good wishes and thank you all for putting up with me as her substitute. David Caress has a question. David, it just disappeared on me.
Oh,
do you want
I just answered the question in typing. It was, when will the acoustic array be deployed? We've only just learned we've got the grant funded. So we're scrambling to figure out whether we can deploy it next summer. And I think we would be able to if COVID wasn't impacting supply chains, but that makes things a little bit uncertain. But we think we will be able to deploy next summer.
Great. Last chance. Thank you all. It's really been a pleasure, and keep up the good work.
Thank you.
All right.
Thank you.
Thanks. Thanks, everybody.
Bye, everyone.
Bye.
It was great.